Hi, I'm Ashley K. Wheeler, and the purpose of this short video is to share with you my most recent project on matroid varieties. It's joint with Jessica Sidman at Mount Holyoke College and Will Travis at the U.S. Naval Academy. So the first question I want to answer is, what is a matroid? And the answer is it's an abstraction of the linearly independent columns of a matrix. So given an R by N matrix A, where R is less than or equal to N, the bases of a matroid on A are the set of R tuples indexing the collections of columns that form bases for the column space of A. We can apply this same definition to a subspace in the Grassmannian, in which case the matroid on a point in the Grassmannian is the matroid on any matrix representing that point. So what's a matroid variety? Well, given a point in the Grassmannian X, let Mx denote the matroid associated to X. What we want to know is what are the subspaces in the Grassmannian Y that satisfy Mx equals My. We call this set gamma sub X, and then the matroid variety on X is the Zariski closure on gamma X. The problem we're interested in is what is the defining ideal for this matroid variety? And I should mention that the defining equations are not obvious because the basis axioms for a matroid give Zariski open conditions. What I mean by that is that bases for a matrix are linearly independent columns. So we're requiring a determinant not to vanish, or we're setting an equation not equal to 0. And for a defining ideal, we set equations equal to 0. So this is what I mean when I say Zariski open conditions. So just to illustrate what can happen, I want to give an example called the pencil matroid. The reason it's called that is because it's 3 lines passing through a point, and my collaborator Will said that points or lines passing through a point are called a pencil. So we have the pencil matroid. This is the matroid on a 3 by 7 matrix with non-bases 1, 2, 7, 3, 4, 7, and 5, 6, 7. So in other words, the columns indexed by 1, 2, and 7 are linearly dependent, as well as the columns indexed by 3, 4, 7, and 5, 6, 7. So what does the picture have to do with this matroid? Well, think of the points as living in projective space. The coordinates for each of these points in P2 give a column of the 3 by 7 matrix. And then also notice that the points are collinear if and only if the corresponding 3 columns are dependent. So we had a non-basis 1, 2, 7, and in the configuration, points 1, 2, and 7 are collinear. Now recall, the homogeneous coordinate ring for the Grassmannian is generated over C. Just imagine that we're working over C, or whatever your favorite field is. But the homogeneous coordinate ring for the Grassmannian is generated by the R by R minors of a generic R by N matrix. The non-bases of the pencil matroid dictate the vanishing of 3 of these generators, and the defining ideal for the matroid variety must contain them. The issue is that it can be shown that the defining ideal has 1 more generator that happens to be a binomial in the generators of the homogeneous coordinate ring. So how do we find this equation? Well, we use what's called the Grassmann-Cayley algebra. And I'll go into more details in the talk, but I just want to say now that the Grassmann-Cayley algebra was invented to do synthetic projective geometry. It's the exterior algebra over the vector space CR, equipped with the 2 operations meet and join. And what it allows you to do is arithmetic on the points themselves in the configuration. And finally, our theorem is about the defining ideal for the matroid variety associated to the point configuration in Pascal's theorem. So Pascal's theorem is a classical theorem from projective geometry that says if you have 6 points on a hexagon joined in a certain way, then the resulting intersection points are collinear. In this point configuration is a matroid variety, and for the defining ideal, we find one quartic, 3 independent cubics, and 3 independent quadrats, besides the generators of the homogeneous coordinate ring of the Grassmannian, given by the collinearities in the configuration. So that's all I want to share for now, and I look forward to seeing you at my talk. Thanks.